Okay. So can you confirm that you can see my screen? Okay, perfect.
It's good, yeah.
All right, so hi everyone. Thank you for being here. Today I'm going to wrap up 5 years of my PhD, 4 years of my PhD into 50 minutes approximately, so please bear with me. The topic we're going to talk about today is the links between meteorology, air quality, and energy along the East Coast of the United States. I'm going to talk about each of these in detail later, and I have worked with Dr. Christina Archer. It's been a pleasure. And today is May the 4th. Yeah. Oops, I don't know why it doesn't work. I'm so sorry. Just a second. All right.
Point it to your computer.
Yeah, it's not working. Okay, anyways. I'm sorry, just a second, everybody. Okay, here we go. Okay. All right. Okay, so today is May the 4th. Here we go. All right, so why East Coast? Let's first start with that. So the focus of my study is going to be this specific area along the East Coast of the United States. And why is that? First of all, it's one of the most populated areas in the United States. And second, the offshore wind energy for the first time is coming to the US, and it's going to come to these specific areas that are shown here along the East Coast of the United States. And it's very exciting. So these areas that you can see here are basically planned or leased by companies. They're planned by the Bureau for Ocean Energy Management. They're along the East Coast. They're going to be hosts for approximately, actually more than 2,000 wind turbines. That's a very big number. And I'm very interested to look at the interactions of these turbines with the atmosphere. And we're going to basically, for the meteorology, we're going to look at these interaction of the wind turbines with the atmosphere. For energy, obviously, we're focusing on the wind energy. Now, another factor that is important about the East Coast is that there are several major ports. So these ports are basically hosts for big ships, actually small ships, so any kind of ships. So they contribute to the pollution in this area, right? Another factor is here, these, as you can see, these little ships here, well, they're not that little. So this area here offshore, we have very major shipping routes in this area that also can contribute to the pollution level. So this is these are 4 factors, 3-4 factors that we're going to focus in the study. So as I mentioned, offshore wind is coming to the United States. The news are coming out, right, every day that what's happening, 30 gigawatts approximately, and at least 30 gigawatts of offshore wind is coming to the East Coast of the United States. Europe has already had these turbines offshore, however, US has not. So we do have the favorable waters, we have the good locations. So this is very exciting. Offshore wind is coming to the US. However, at the same time, controversial news are coming out that, okay, what are going to be the impacts of these turbines on coastal communities? How are they going to impact really the wind or the temperature? What about us? Like, what's going to happen? Like, how are we going to feel it? So this is the focus of this study here, the meteorology part of this study. In my dissertation, I have answered 5 questions. However, today because of the time constraint, I'm gonna focus probably on 3 of them, and if we have time, I can just give you the results of the other 2. So, all right, let's get started. For the first question, here I am interested in looking at how do these extreme scale wind turbines that are coming to the United States and specifically the East Coast are going to impact the meteorology along the East Coast, right? So we're going to answer this question here. Okay, so how can they even change meteorology? Like, why are we even interested in that? Well, wind turbines can alter meteorological factors such as wind speed or temperature through the wakes. Now let's learn what wakes are. Well, a lot of people would probably know about this, but I'm just going to introduce it quickly. So wakes are these plume-like volumes behind the wind turbines, and they are normally associated with lower wind speed. They have higher turbulence, and they're generated within the rotor area. However, they can extend or vary in magnitude depending on different factors in the atmosphere, such as turbulence or atmospheric stability. Now, what is atmospheric stability? Actually, I can't really teach atmospheric stability here because it's a very big concept. However, I'm gonna just give a quick introduction to it. So atmosphere can be in actually four different conditions. So first, condition is neutral atmospheric conditions, and then we have unstable, stable, and sometimes there's an inversion happening that I'm going to explain now. So in the atmosphere, the temperature is expected to decrease by height. So there's a specific elapse rate, we call it, that is for dry air 9.8 kelvins per kilometer. In this case, if this is happening, the atmosphere is basically neutral. This is one way to determine it, not the only way though. So however, the air basically can cool down way faster, right? So the temperature can drop faster. In this case, the elapse rate is lower and the atmosphere is unstable. In this situation, the heat fluxes are upwards. So this is important to know. Next, the atmosphere can cool down a little slower and the elapse rate is higher. In this case, the atmosphere is stable and the heat fluxes are downwards. And it's very important to note that the heat fluxes are downward because we're gonna see this later again. And it could be so stable that in some cases, actually the temperature increases by height. So in this case, warm air is above the cold air and atmosphere is, there's an inversion happening. The heat fluxes are again downwards. All right, so what has been done in the literature so far? Actually, there has been studies that have looked at the impact of wind turbines on the surface properties before. They have reported warming in presence of the turbines in stable atmospheric conditions at the surface, and they have also reported cooling during unstable atmospheric conditions at the surface. However, the gap between the literature was that all these studies, first of all, so none of these studies have really focused on the East Coast of the United States and the offshore wind areas that are coming to the US. And the second factor is that they have all considered a turbine that was basically at the time that was out at the time of that study. However, this technology is growing fast and fast. So none of them have really used the turbines that we have used in this study that are very tall. All right, how do we even do this? How do we look at how turbines change the meteorology in the area? Well, they are not built yet, right? So we can't measure them. The only way that we can look at this is through simulation. So we have to simulate these turbines in numerical models. So for this specific study, I have used the weather research and forecasting model, WRF model. It's been developed at the National Center for Atmospheric Research. The WRF model is a very complicated model, actually, and basically it's used for both research and forecasting. So it's a 3D gridded model, right? So the grid looks something like this here that you can see from the top. However, in 3D, it looks something like this. Basically, it's gridded and horizontal, and it's important to know that there are also layers in the vertical. So when we place a turbine in a grid cell, for example, the turbine includes several vertical layers, but also it is like within a horizontal grid cell. All right, so in my simulations, I have covered 3 months of summer in 2018. I have 35 vertical layers, and from which 8 of them are within the rotor area of the turbines and 4 are below the rotor area of the turbines. So also, it's also important to note that the WRF model, as I mentioned, it's a very complicated model. I'm not going to go into details. However, it's basically it's made of two important parts. One is the WRF pre-processing system, which basically prepares the geographical and graded and geological data into the core model, which is the WRF model itself later. All right, so here, okay, this is the domain of my study, basically. I have focused on this big domain here. It's covering the whole US East Coast. Let me see if my pointer works well, right. It has a resolution of 4 kilometers. However, I also have two fine domains, they're basically separate nested domains within that domain that cover the wind farm areas. And I have basically zoomed into them in here. These little areas are the wind turbines, and the resolution of the fine domains are 1.3 kilometers. Okay, it's also important to note that I use the two-way nesting simulations in which these fine domains are actually interacting with the mother domain. Okay, the turbine I have used in the study was the DTU 10 megawatt turbine. It has a hop height at 119 meters. The diameter is 178 meters. Here you can see the power curve and the thrust coefficient curve for this turbine. The number of the turbine in every wind energy area that I showed in the beginning of this presentation is based on the state target. So every state has a target for 2030. I have used that to understand how many turbines we need for that area. And the placement is such that I have started closest to the shore and I have moved further and further. Oh, okay. All right, so now let's understand a little bit how these wind turbines are really modeled in these numerical models. Well, the grid cells of such numerical models that I'm using here is in order of kilometers, right? However, the turbines are in order of meters. So it's computationally impossible to go to high resolutions, basically high enough resolutions to be able to see the rotation of the blades and basically to resolve every variable around the turbine. So it's impossible. What do we do then? We have to use a method called parameterization. So we parameterize these turbines in the model. And that's basically kind of like a little model inside the big model, right? So we look at the cumulative impact of these turbines altogether in that grid cell. Basically, we look at the cumulative impact based on the mean variables in that grid cell. So for example, in this study, I'm using the Fitch parameterization. In Fitch parameterization, the turbines are treated as a sink for momentum, and they are also a source for turbulent kinetic energy. What happens here is the wind, upstream wind, basically undisturbed, is hitting the turbine. The turbine extracts energy and momentum from the wind, and the remaining wind looks something like this. Basically, this is the wind profile behind the turbine. This is obviously approximately, you know, it's not exact. And this is kind of like the wake that we talked about, right? There's more turbulence and there's lower wind speeds. Okay, so this is the only slide with equations, I promise. In the Fitch parameterization, we just need to know that every turbine basically induces a drag force into the atmosphere. The drag force is calculated by this first equation here, and it's related to the thrust coefficient of the turbine. However, based on the drag that a turbine induces on the atmosphere, it's extracting some power or some energy from the wind, right? That power that is extracted from the wind is calculated by this equation, again related to the thrust coefficient, and it's related to the cube of the wind speed. So note how important it is to estimate the wind speed accurately at the hop height, right? However, this extracted power, you know, not all of it turns really into electricity, right? Some of it is lost. The amount that is turned into electricity is calculated by this equation here. It's the same equation, but it's using the power coefficient of the turbine. So now power coefficient and the thrust coefficient are some manufacturing characteristics of the turbine and basically define the efficiency of the turbine, right? So what happens to the rest of this energy? We extracted some, we turned some into electricity. The rest in phase parameterization turns into turbulence in the atmosphere. And that's why we calculate the turbulence coefficient through this equation here, which is thrust coefficient minus power coefficient. And, you know, we use also some corrections that I can explain them later if anybody is interested. Okay, so to see the impact of the wind turbines on the atmosphere, we do two sets of simulations, one with no farms at all, one with including the farms. So the same exact setup, this is the only difference. The difference between them are going to give us the net impacts, right? Okay. So now let's look at some findings that I have basically found throughout previous years. For this study, I'm going to focus on wind speed. I'm going to focus on more like turbulent kinetic energy. And then we're going to look at surface temperatures and heat fluxes, and if we have time, some moisture content. Okay, so first, I'm going to explain the impact of the wind farms on the wind speed. So this plot that you see here is basically showing us the wind speed changes in presence of the wind turbines. However, this is calculated at the hub height of the wind turbines. And this specific day, basically you can see the changes to wind speed at every hour. This is a specific day, August 2nd, that we detected the longest wake that traveled up to 150 kilometers. That's a very long distance, actually. And the atmosphere was stable during this day. However, you know, you can see that even in the highest impact day, the wake doesn't, because of the dominant wind direction, that is southwesterly, the wake doesn't really hit the land a little bit in Long Island and in Massachusetts, but this is again at the hub height. We should look at the surface. Okay, so from now on, I'm going to focus on the average changes to different variables, not just one day. So these results have been averaged through 3 months of simulations. So here again, we started with the wind speed. The wind speed at the hub height is the plot at the left, and the wind speed changes at the surface is the plot at the right. So on average, the wake basically extends up to 50 kilometers, and there's a wind speed decrease by 2 meters per second. However, this wake extends to the surface and it reaches the surface, and within the farms, it is causing a wind speed deficit of 0.5 meters per second. But if you see this plot, which is the changes at the surface, it doesn't really impact the coastal areas, right? On average, we don't have any impacts on the coastal areas. The same results for domain 3. Basically, they are very similar results to domain 2. So from now on, I'm mostly gonna talk about domain 2. Okay, the next variable that I have looked at is the friction velocity. Friction velocity is also decreased at the surface in presence of the wind farms in both domains. And as expected, well, because the wind shear is decreased closer to the surface in presence of the farms, the TKE is also decreased at the surface. However, the TKE, as you can see here, is way higher at the tip of the rotor area. This is the top of the wind turbine, and that's where the most TKE is added to the atmosphere. So we can see that it's significantly increased at the top. Okay, the next variable that I'm gonna talk about is the temperature changes. This is probably the most important one, and it's been more debated in the literature. So let's see what we find here. All right, I have looked at the changes to the temperature in 3 different heights in the atmosphere. One is above the wind turbine, or basically the tip of the rotor area, which I have shown here. It's like this area on top. Here we see a decrease in temperature. Temperature drops on top by approximately 0.5 degrees. However, the temperature is increased within the rotor area, but below the hub height, that would be here. And finally, the temperature is actually decreased at the surface. So this is the most important one that we care about, right? We want to see how temperature really changed at the surface, and we find a slight cooling. However, it's the magnitude is kind of negligible. It's like 0.0 degrees. We can really say there are no changes, but we're gonna look at these changes and to explain them a little better later for just, physics sake and understand what's going on in here. Okay, so the mechanism that I believe that is causing this, this is not my work. This work was our lab mates and Dr. Archer's work. So I'm just going to explain. I believe that this mechanism also applies here. So I am focusing on the stable atmospheric conditions because that is when we see the highest impact, right? Okay, so as I explained before, in the stable atmospheric conditions, we have downward heat fluxes, right? So this is upstream, right before the air basically hits the turbine. What happens once it hits the turbine is that there's a wake right behind the turbine. So we just talked about that inside the wake, there's higher turbulence, right? Added turbulence and lower wind speed. So this added turbulence in the wake of the wind turbine causes basically makes these heat fluxes to be stronger. So we have enhanced heat fluxes that are downward. These heat fluxes are bringing the heat down, right, to the surface. So basically, we have a divergence of heat fluxes aloft, and we have the convergence of these heat fluxes at the surface. So this mechanism perfectly explains why everyone has found warming in the literature at the surface. So, but what do we find in here? Well, I have a cross-section of the temperature changes in my study. Basically, this cross-section has been taken through this red line. So as you can see in this cross-section, okay, let me explain a little first that the y-axis is the height and the x-axis is basically the horizontal here, lats and lons. And the box here shows the location of the wind turbines. Here we have the hub height and tip and the lower part of the wind turbine. Okay, so in this cross-section, you can see that we can still see the warming. The warming is still happening within the rotor area. However, we don't see that warming is stretching to the surface, and instead we see some cooling at the surface, right? Okay, let's see why is this happening. So there are two hypotheses here that I believe it's true. Well, they're just hypotheses. I'm going to work on it. So one of them is that I believe that the decrease in heat fluxes at the surface, the reduction of the heat fluxes at the surface is causing this cooling at the surface. And the other one is in presence of the taller wind turbines that we study here, the warming happens, but it just remains lifted. It doesn't stretch all the way to the surface. Now, let's see if these hypotheses are true. Well, I first have looked at changes to heat fluxes at the surface. I picked just one location. Here in this location, you can see that in a stable atmospheric conditions, when the heat fluxes were negative, the changes to heat fluxes were actually positive. So what it means is that the heat fluxes are reduced in magnitude, right? So this location proves that heat fluxes were decreased, in fact, at the surface. Now, let's see if this is true for the whole domain. Basically, I've tried this hypothesis in domain. You can see that the median heat fluxes throughout the 3 months were blue. It means that they were negative and downwards. So the atmosphere were like majority of the time is stable. And the changes to heat fluxes at the same time were positive. It means that the heat fluxes, yes, in presence of wind farms, the heat fluxes were decreased in magnitude, right? So let's see if that matches with our changes in temperature. You can see here that, well, these two kind of like spatially match. We have a spatial correlation, good spatial correlation between the changes to heat fluxes at the surface and changes to temperature at the surface. So it means that this can be a reason. This is the reason actually why we see the cooling at the surface instead of warming. Now, let's test the second hypothesis. So I believe that the height of the turbine has something to do with these changes and actually is playing a significant role. Let's try this. So to try this hypothesis, I basically conducted 2 separate simulations. I picked a 1 week period in 3 months in which the atmosphere was stable. So throughout this 1 week, I repeated the simulation, exact same setup, one with 10 megawatt turbine with hub height at 120 meter, and one with shorter turbine that mostly have been studied in previous research with 80 meter turbine, 80 meter hub height. So you can see that from the results here, you can see that with the shorter turbine, the warming within the rotor area actually stretches all the way down to the surface, and it does cause a slight warming at the surface, as consistent with the literature, right, as everyone else has found. However, what happens here is that with the taller turbine, that warming doesn't reach to the surface anymore, and it's just basically it stays aloft and it doesn't reach to the surface. Instead, the reduction in heat fluxes that we just defined are causing a slight cooling at the surface. So I have to mention here that this was actually a very important finding. This is the first time we discovered this. Basically, no one really has talked about the height of the turbine that could have or reverse the impact at the surface. Okay, now one may ask, you just tried one tall turbine, how do you know that it was really the height of the turbine that mattered, right? So I conducted another set of simulations. This is another 1 week long simulation, the same time, same setup. However, this time I used an even taller turbine, which is the NREL 15 megawatt turbine. Basically, it's just designed yet, it's not out, but the hub height is actually at 150 meters this time. It's way taller. So with the repeated simulations, you can see that the even taller turbine, which we call here the extreme scale turbine, has the same results as the previous tall turbine. So we still see the cooling at the surface and the warming within the rotor area. And the differences are obviously because of the height of the rotor area. So basically this showed that with even taller turbines, we're going to see the same results. All right, I think I have to, okay. All right, finally, we're getting to the conclusion of this section. Here we had 5 questions, right? We answered the first question of this research. How do the extreme scale offshore wind turbines alter the meteorology along the East Coast? So we looked at the wind speed. The wind speed decreases strongly at the hub height. However, it decreases only by 0.5 meters per second at the surface, and it doesn't reach the coastal areas of the East Coast. The temperature, we see slight cooling at the surface. But basically the magnitude is very small. It's kind of like intangible to humans, really. And the turbulent kinetic energy and the friction velocity are reduced at the surface, but turbulence is way higher at the tip of the rotor area. However, well, I mentioned that the meteorological impacts at the surface are intangible to humans along the East Coast. And it's also important to note that the highest impacts were during the stable atmospheric conditions. Okay, to complete this study, okay, I'm just going to briefly note the second question of my research because of the time constraint. I'm not going to go into detail here, but one factor that can impact the wind speed estimations at the hub height of the wind turbines is the surface roughness. It's the surface properties that is basically playing an important role in wind speed prediction. So I conducted a study I looked at 3 different methods used in the literature. Basically, I looked at what method is doing the best, and through that method, I predicted the best value, best representative value at the East Coast for the surface roughness length. And for this, basically, I used the measurements from 2 campaigns at Nantucket Sound, and yeah, I verified that this value of 0.006 meters for surface roughness is doing the best. So the important thing is, next, I looked at my model, the WRF model, to see what surface roughness length is used there, and it was 0.01 meters. So these 2 values were actually very similar. So we confirmed that the model is actually using, basically is matching what we found for this area. And here this plot shows how close the results are for 2 different surface roughnesses. All right. Okay, let's move on to the next section of this dissertation. So the next section, we're done with the meteorology, right? The next section, we're going to focus on air quality. I have to emphasize here, why air quality? Because air quality still harms people across the United States and across the world. Some pollutants are like nitrogen dioxide or particulate matter. They can, once you breathe them, they can enter your lungs, and from there they can directly enter your bloodstream and basically can cause dangerous harms to humans. Also, it contributes to climate change and global warming, which I believe that we have to take action now if we want to do something. It's time. All right, so in this section, we're going to look at 3 different topics that contribute to the air pollution at the East Coast. So one is the wind farm. So far we learned how the wind farms altered the meteorology along the East Coast. Next, we're going to see how these changes in meteorological factors like wind speed or temperature are going to change the pollution levels in this area. Next, I'm going to talk about the shipping emissions. And basically, this is going to be, I'm going to dedicate most of this section to shipping emissions and the pollution that we see from the ships along the East Coast. And finally, the COVID-19 pandemic. So an event or basically an event that happened throughout my PhD, one of the most important ones, it was unfortunately the COVID-19 pandemic. And it was a very unfortunate event. However, it was a very good opportunity, and basically it was a natural experiment that was happening across the United States to reduce the human mobility and basically the traffic, because you can't really like conduct this experiment. You can come and like decrease the traffic by like, for example, up to 60% that we're going to see here. This happened naturally, and I took advantage of this to understand how the pollution levels changed during the COVID-19 pandemic. However, again, unfortunately, because of time constraint, I'm just going to give you a quick, brief result of the of our findings. All right, so for this section, again, I'm taking a modeling approach. I'm going to use the comprehensive air quality model with extensions called CAMEX. It's a 3D chemistry model. It's approved by the Environmental Protection Agency, and its performance has been verified in the literature several times. All right, here's a diagram of the CAMEX model. So it's a very complicated air quality model, actually, but it also requires a few input data, right? The first important one is the emissions. We need to get emission data from different sectors to input into the model. So I have received my emission data from the National Emission Inventory for this study. We use several preprocessors to make the data ready for the model. The next is the meteorology. So meteorology actually plays a very important role in air pollution in different areas. So our inputs are coming from the WRF model that we just discussed in previous section. And then there's the photolysis rates that we need the data to input to the model. And finally, the initial and boundary conditions. All right, so remember we had 5 questions. So we went through 2 of them. Now we're going to focus on the 3rd question. Now I'm interested in looking at if the meteorological changes induced by the wind farms in the atmosphere is going to change the air quality in the area. So for this, again, I'm taking the same approach. We have 2 sets of simulations, pollution with no turbines and pollution with turbines. And please note that the only way that the turbines can actually contribute directly to the pollution level is through the changes to the meteorology, right? Because they don't emit, they don't have emissions. All right, so did they really impact the air quality? Well, the quick answer is not really, but let's go into the details. So here I'm going to focus on ozone, which is also a very dangerous pollutant, ground level ozone at the surface. And I'm going to focus on particulate matter, fine particulate matter. And I'm going to see how they change in presence of turbines. So the ozone was increased, but I'm not sure if you can even notice in this plot, it's increased by up to 0.2 ppb. That's a very, very small amount. actually, and the increase is only within the farms and nothing along the east coast of the US. I mean, coastal areas of the US. The next pollutant is particulate matter, fine particulate matter. It was also increased by a little higher. It was like just 1 micrograms per cubic meter, but the increase was offshore and it did not reach the land. Basically, it didn't impact the land. It just remained offshore. The other pollutants that I've looked at that are not shown here was nitrogen dioxide and sulfur dioxide. And the wind farms basically didn't have any impact on those pollutants, so I don't have it here. All right, so on average, they increased some pollutants by just a very small amount, but the impacts did not reach the coast, and the other 2 pollutants were not changed at all. All right, now we're getting to the 4th question. Here we're going to look at how ships are impacting the air pollution in the coastal areas of the United States. Okay, so let me just show you the motivation I have like for this project. Let me see if I can, yeah. Okay, so here I have a map, I have a live map of shipping routes, shipping activities right now that is happening here. So you can see every dot here is a ship basically, right? So we zoom in here to the United States. My domain of study, my interest is again East Coast, and you can see that a lot of ships are coming in and going out, and there are major ports. So this was my motivation, and I was like, there's a lot of ships. Well, a lot of other sectors have been already studied in the literature. So what about the ships, which also have been studied? However, we're going to look at them in high resolutions, and we're going to focus on different pollutants. All right, let me see. No. Okay, that's fine. Okay. All right, so the emissions that I have used for the shipping pollution, basically I have got it from EPA. It's a national emission inventory. It's important to note that emissions could be of 2 types. One is the area sources, they're like 2-dimensional, and one is point sources. Now, the shipping emissions in the EPA inventory, national emission inventory, are from the 2nd type, and they are point sources. This is actually very important because it allows us to calculate for plume rise, and we have the information about the stack parameters of the ships here. So here, let me give you a quick overview. Okay. I hope you can see. Okay. We have it here, for example, if you consider this a stack here, this is the actual stack height of, for example, a ship, right? However, what we care about is the effective stack height, which is the actual stack height plus the plume rise, because the plume, well, rises a little bit before it enters the atmosphere, and that's important. And that is because it's going to let us understand at what vertical level the pollutions are entering the atmosphere. Now, why is this important? Again, we're going to go back to the atmospheric stability. This is important because atmospheric stability plays an important role again in transport, or basically on behavior of these plumes and pollutants. For example, in this plot here, you can see how these plumes are behaving in different atmospheric stabilities. I'm not going to go into detail, but it's important to know, for example, if there's an inversion layer, and if a pollution is entering the atmosphere below the inversion layer, it's going to reach the ground, it's going to get trapped, and it's going to reach the ground fast. It's very dangerous. If it's released above the inversion layer, it's basically going to get trapped above, and it's going to travel long distances before it reaches the ground. Okay, so for this section, I'm going to focus on 4 pollutants: ozone, nitrogen dioxide, sulfur dioxide, and fine particulate matter. These are all regulated pollutants by EPA. dangers for human health. So this table here shows how EPA basically, from a policy standpoint, how we need to calculate the concentrations of these pollutants in the atmosphere to understand if a location is an attainment or non-attainment with EPA standards. So here in my results, I'm going to look at the results from two perspectives. One is from EPA standard perspective, which is a policy standpoint. And second, I'm going to look at the maximum contribution that the ships can, in a worst case scenario, contribute in a grid cell. Okay, so let's start with ozone. Here, the animation that you can see on the left is basically showing the 3-month average of ozone in my domain, but these are average at every hour. You can see the diurnal cycle. It's important to note that ozone is very sensitive to temperature and sunlight. Oops, sorry. To temperature and sunlight, and that's why ozone is the highest during the daytime. Sorry if this works. Excuse me. Okay. So the animation basically is showing us the map of the diurnal cycle in different locations. This graph here is a spaghetti plot. Basically, it's showing the ozone concentrations in a location in every day. And you can see here also that in some time during the day, the ozone actually goes up significantly, and during the nighttime, it comes down. So our focus is going to be the daytime because that's the most important time of the day for ozone, right? Okay, so we saw the ozone concentrations already in the background. So basically this is the ozone concentrations in the domain. Now, the middle plot is showing the contribution of the ships to ozone pollution from a policy standpoint. So this is very complicated. It's basically, I'm going to try to explain it. You basically, it's important to know the daily maximum of ozone. So there's a maximum of ozone every day, right? We have this for a whole year. We pick the 4th highest one, and we have to average it through 3 years to understand it from policy perspective. So here we didn't have the 3 years, and I'm just focusing on 3 months of summer. So the middle plot shows the contribution of the ships to ozone from a policy perspective. Again, you can see that ozone has been increased in presence of the ships, offshore mostly. However, it's also the ships are impacting some coastal areas here in Virginia and North Carolina, and also some parts of Massachusetts. But interestingly and strangely, there are some locations that are blue and basically with negative values. What's happening there is it means that in presence of the ships, the ozone is actually decreased in those areas. All right, the next plot here is showing the maximum contribution. So the worst case scenario that can happen in presence of the ships. Again, the ozone concentrations are increased by up to 7 ppbs offshore and some parts of the land. However, again, you can see these blue areas along the East Coast, which basically are suggesting that ozone has been decreased in presence of the ships in those areas. Those are mostly urban areas. Those are like big cities or urban areas. Now, what is special about these is, so first we need to learn a little about ozone and ozone production. So ozone is actually very sensitive, as I mentioned, to temperature and sunlight, but it's also very sensitive to volatile organic carbons in the atmosphere and also to nitrogen oxides in the atmosphere. So the ratio between these two basically shows us which one matters for ozone production. If the ratio is low, it means that there's low volatile organic carbon in the atmosphere. Ozone is sensitive to the amount of VOCs. So, you know, the increase of ozone is happening by increase of VOCs. This is the case of urban areas and the places that we just noticed. In the model, this ratio is calculated by, you know, some other ratio that I have shown in here. And you can see that the areas with like that are lighter and yellow, basically, and orange, they are VOC limited and sensitive to VOC and not NOxes. All right. So what happens here is in urban areas that are VOC limited, the NOxes or nitrogen oxide is basically acting as a agent to destruct ozone, to basically scavenge ozone. So in presence of extra nitrogen oxides, ozone is actually destructed in these areas. Let's see if nitrogen oxides were actually up. And here, I'm a little early on the slide, but you can see that this is the base, basically the nitrogen, oh, I'm sorry. These are nitrogen dioxides. I'm sorry for the captions. So nitrogen dioxide from a policy perspective is increased in the coastal areas and along the coastal areas and in major ports. From a maximum contribution perspective, again, nitrogen dioxide is increased significantly along the coastal areas. So yes, nitrogen dioxide was increased where we saw those decrease in ozone values. And you can see that the pattern of ozone reduction also matches very well with the spots that the nitrogen oxide or nitrogen dioxide were increased. So it tells us basically that these areas were VOC limited and nitrogen oxide basically destructed ozone in presence of the ships. So this is the reason why it decreased. And I'm sorry for the captions. So for particulate matter, again, you can see the base in here on the left. The middle plot is from a policy perspective. Particulate matters were increased in presence of the ships, but they don't really impact the coastal areas. I mean, they do, but depending on in what condition every state is. If they are very close to being non-attainment, this is important because the ships contribute to approximately 1 to 2 micrograms per cubic meter of particulate matter in some states. And this is the maximum contribution here that you can see that is very high. All right, SO2, sulfur dioxide. The left-hand side plot is actually very interesting. Is because this is also averaged over 3 months at every hour. It's showing how the increase in sulfur dioxide is actually very similar to kind of like a shipping route. So it shows us how much ships are contributing to the sulfur dioxide amounts. It's actually very high in the area. And the middle plot shows it from the policy perspective. Again, it's increased along the coastal areas. And the contribution of the ships is actually very high to sulfur dioxide. All right. So with that, I'm going to jump to the last question of this presentation. Again, because of the time constraint, I'm not going to go into the details. During the COVID-19 pandemic, the traffic was significantly decreased in the United States. So did the air quality really improve? The question is, was the air quality better? Well, the answer is it depends. It really depends on what pollutants you're looking at. It's very complicated. This project is part of a way bigger project. Here, some results are still inconclusive. For example, if you're talking about nitrogen dioxide, it was definitely decreased across the United States. As you can see here on the top plot, these blue areas and along the major highways, you can kind of see the also highways in here. So nitrogen dioxide was decreased. PM 2.5, I would say, was inconclusive because with the modeling results, we still can't conclude this because we don't have enough data and emission data. However, the preliminary results of our previous study showed that PM2.5 didn't increase, and in fact, it increased in some places. And that's because, well, some different factors can contribute to it. For example, different emission sectors that we don't have the data for, so it's inconclusive. Also, ozone, very similar to the ships, was increased in urban areas and decreased in other areas. So these red dots that you can see here are the places that matches very well with where nitrogen dioxide was decreased. So the same story. All right, in conclusion, we checked the wind farms if they contribute to pollution level, and the result was that depending on the pollutant we're talking about, for ozone, it was negligible. For particulate matter, it was up to 1 micrograms per cubic meter. Only offshore, they don't reach the coastal areas. For shipping pollution, again, for ozone, it depends on the location. Ships can increase or decrease ozone level in different areas. Nitrogen oxides were definitely increased. Sulfur dioxide was definitely increased. And also particulate matter was increased in presence of the ships. However, again, impacts in the coastal areas depends on the pollutant itself. And for COVID-19, we just talked about it. Some pollutant is inconclusive, but NOxes were decreased. Ozone, again, depending on urban or rural area, could increase or decrease. All right, and finally, I would like to acknowledge, first of all, my committee members. First of all, Dr. Christina Archer here, that has supported me enormously, like during the past 5 years. It has been amazing, not just student professor, it's been a friendship. Dr. Diana Veron, thank you so much during the COVID-19 pandemic. It was hard, but we got in contact and it was very valuable. Dr. Stefano Alessandrini that hosted me at NCAR, and I learned so much. And finally, Dr. James Corbett that has had invaluable comments for my project and has helped me a lot through the air quality project. And I would like to acknowledge DENREC for the funding, School of Marine Science and Policy, the UD Graduate College for the doctoral fellowship during my PhD. And finally, I would like to mention some people that I have been so far away from them for several years. Excuse me. And my partner here, Logan, and my friends that we've been together so much, but I couldn't find a single picture with all of us together. So. All right, thank you so much everyone for listening, and with that I'll take any questions, and I'm sorry if it was a little longer than expected. I had so many things to talk about.